Welcome, Calculus AB. This is section 3.2, Rolle's theorem and the mean value theorem. The essential question is, what is the relation between Rolle's theorem and the mean value theorem? Let's begin. So in the last section, we talked about the extreme value theorem, and this is where a continuous function, you're on a closed interval AB, must have a minimum and a maximum. So it looks something like this. I have a closed interval. I'm going to call this, shift this down a little bit. This is A to B. Okay? So if it's on this interval and we have some function, it starts whatever here for A, so whatever here for B. There's going to be some point that's a maximum and some point that's minimum. In this case, this function, that's my max. And down here would be my minimum. All right? Now, Rolle's theorem is similar to this, and it guarantees an extreme value inside the closed interval. So there's going to be one inside, just it doesn't have to be on the endpoints. So here's Rolle's theorem. So let's say f is a continuous function on the closed interval AB and differential on the open interval AB. That means everywhere except for AB. If f of A equals f of B, that means there's at least one number in AB that f prime of C is equal to 0. So basically, if you have let's draw a picture of this. If I have A to B and I have some function here, and I'm saying if the f of A, so this is your A right here is going to be a point, and that's A and f of A, and let's say equals f of B. So basically they have the same y values are the same. I can be whatever. Say that's the function. That means there's some number in there where the derivative at that value, we can call this C. That's where f prime of C is going to be 0. Basically it's going to be a tangent line. And in this case, if you're looking at this graph, where a tangent line is going to be 0 would be like right up here. So this could be a C. So this is kind of neat, and we'll do a proof of this in class. So if you have any closed interval here, and the y values are equal to each other at the endpoints, then there's going to be somewhere where the derivative evaluates to 0. All right, let's use that in an example. Let's talk about this a little bit more. So here's another picture illustrating that. So if I have 2 points A and B and they have the same y value D, we have a relative maximum right up here at C, and then the tangent line, the slope is 0. Now, if you don't have that part where everything has to be differentiable, then you'll still have critical numbers at C, like in this case, but this is not differentiable, so we don't have a slope of 0. This would be one of those undefined derivatives. Let's take an example. So I want to find two intercepts of this function right here and show that f prime of x equals 0 at some point between the two x-intercepts. Okay, so first, what does it ask me? Find the two x-intercepts. X-intercepts happen when y equals 0. So what I'm going to do is take this function f of x. I'm actually factor this, and it factors out to x plus 3 times x minus 1. And that's setting, y or f of x equals 0. So 0 equals x plus 3 times x minus 1. That means my two x-intercepts are when x equals negative 3 and positive 1. That's my x-intercepts. Okay, so we have to find that f prime of x equals 0 at some point between negative 3 and 1. So my f prime of x, derivative of that's going to be 2x minus 3. And where that f prime of x is going to be 0, so 0 equals 2x minus 3. And solving for x, add 3 to both sides. You will get 2x equals 3. Divide by 2. And you get x equals 3 halves. And 3 halves is between negative 3 and 1, so there's your proof right there. All right, Rolle's theorem can also be used to prove something called the mean value theorem. And some people say that this is one of the most important theorems in calculus here, so pay attention to this. So it says f is continuous on a closed interval AB and differentiable on the open interval, just like Rolle's. There exists a number C in AB such that the f prime of C equals this right here, and f of B minus f of A over B minus A. What is that? You might have seen this before. This is like the slope. Think of this like the slope between 2 points. If I did the y1 minus y2 over x1 minus x2, think of this kind of like the slope between 2 points. So what we're saying is if we have 2 points A and B, slope between 2 points, and let's say point A is right here. So this is your f of A. And let's say point B is right here. And we're going, this is f of B. We're saying that you might have a function that looks like this. Whatever this function looks like, it can look like a curve like this, or whatever. The slope between those 2 points right there which would be f of b minus f of a over b minus a. So the slope of this line is going to equal to the slope of some tangent line on here. And I don't know where that tangent line is, but it's going to be somewhere. So I could take this line and make another copy, and it'll be tangent to somewhere on that graph. So that's kind of neat. So we know that if it's kind of a neat property right there, we can actually apply that to a few things. So let's take an example. F of x equals 5 minus 4 over x. We want to find all the values of c on the open interval 1, 4, such that, in this case, with the mean value theorem. All right. So what I want to do first is I want to see what f prime of c actually evaluates to here. So I'm going to just start plugging in. You got f of 4, you'll get, so f of 4, you get 5 minus 4 over 4, so 5 minus 1, which will be 4, minus f of 1, 5 minus 4 over 1, so 5 minus 4 would be 1, over 4 minus 1. And if you plug those things in, you will get 3 over 3, which is 1. So my f prime of c equals 1. I want to find some value for c where that's true. Basically, what it's asking is, where is the derivative of this f of x function going to equal 1? All right, so let's figure out what f prime of x is. F prime of x is going to be 5 minus 4 over x, so it's the derivative, if you want to write that differently, 5 minus 4 over x. Derivative of negative 4 over x is going to be positive 4 over x squared. All right, so where is that going to equal 1? So we want to find out where that equals 1, so 1 equals 4 over x squared. And another way to write that is going to multiply both sides by x squared. So you get x squared equals 4. And that means your x values is going to be plus and minus 2. Now notice it has to be on the interval 1 to 4. So negative 2 doesn't work. The only value for c that works is when or c equals 2. Not when c equals negative 2 because it's not on that interval. All right, and we can look at a graph of this case. So here's the graph of that function, and we're going from 1 to 4. And the only point right there, so we have a slope from 1 to 4 right here. That 0.23 right here, the slope of the line tangent is the same slope as between points 1, where x is 1 and y is 4. All right, that's it.